Hello, everyone. Thank you for coming. My name is Connor Walsh. I will be hosting the Time Complexity and Big O Notation workshop for the SUNY Albany IEEE Student Branch. All right. So, why would you want to understand time complexity? For starters, so you can pass CSI 210, 213, and 403. Understanding time complexity is important for any programmer because it allows you to compare and contrast different algorithms and let you discover which would be more efficient and why it would be. When programming, ideally, you would want your code to take the least amount of time and use the least amount of system resources. So, by understanding time complexity, you can accomplish that and get a good grade or a promotion. So, what is time complexity? Simply put, time complexity is a way to represent the amount of time that an algorithm will take. Time complexity is represented in big O notation. The most common examples are O of 1, which is constant time, O of log n, which is logarithmic time, and O of n, linear, and O of n squared, which would be called quadratic time. So compared, O of 1 is your best case, meaning it is constant and will always run at the same speed. O of log n is pretty fast. It is most commonly seen in binary search. O of n is linear, meaning the input is pretty much going to directly correspond to the output. And O of n squared is quadratic time, which is not very good. As you can see in this big O complexity chart, down here, all your good ones, O of 1, O of log n, O of n. Then you start to go up here, and you start to see O of n log n, which we're not going to cover. And then you see O of n squared, which is up here in the horrible tier. And then there's factorial. We're not going to go there. So, O of 1 is constant. A time complexity of O of 1 means that no matter what the input is, the code will always execute in the same amount of time. Ideally, you want your code to be as close to O of 1 as possible. I'm going to have some examples for all of these time complexities to make it very easy to understand. If you have any questions at any time, don't hesitate to ask. So here's an example. O of 1 is very straightforward. So in this Python code that I wrote out here, this is a function. So whatever you pass it, right? You pass it an array of nums and an index to print. No matter how big the array is or the size of n, it will always be only looking up for one array location and printing out the value. So I'm going to show you here. I'm going to have to switch the stream over to, hold on. Here we are. So here is some sample code that I wrote out for constant. So as you'll see, I have 3 separate lists of different sizes. So there's going to be one list of size 10, one of size 1,000, and one of size 100,000. And we're going to run this code 100,000 times for each of them. And it's going to keep track of the time it takes for all of them to run. So if I run down here, so it's going to print them all out. So hold on 1 second. And now it'll show you the time it took. So for printing out, for printing out from a length 10 array 100,000 times, it took 1.38 seconds. For printing out from a 1,000 length array 100,000 times, it took 1.36 seconds. For printing out from a 100,000 size 10,000 times, it took 1.27. So you can see they're roughly the same. There's going to be some differences because Python is very resource intensive and not very fast. So roughly, they're all about the same exact time. So if I run it again, it should be the same exact thing. So basically, it shows that no matter the size of your input, you're always going to get roughly the same speed here with slight variation due to Python being pretty slow. So now I'll bounce back into the slides. Okay, everyone can see it still? Looks good, right?
I see it.
Okay, good. All right, so now we'll go to logarithmic time. O of log n is slower than O of 1, but faster than O of n. The most common place you will see O of log n is the ever-popular binary search algorithm. For the most part, divide and conquer style algorithms will be O of log n, because you won't need to search every entry, rather decide where you don't need to search. For this one, I will also have a code example and a picture example. So I'm going to show you this. This is the binary search algorithm, which you probably learned, I think, what, 210, maybe 213? If you haven't taken it yet, it's relatively simple. So you pass it an array, a lower bound, an upper bound, and what you're searching for. And this is a recursive example of it. There's an iterative one, but it's much easier to understand the recursive one. So basically, if I show you this, it will be much simpler, right? So if you pass it this array, binary search starts in the middle and basically decides, oh, and I should mention that binary search only works on sorted arrays. If it's unsorted, you have to sort it first. So binary search starts in the middle. So it says, if you're looking for 7, right, it goes, okay, we'll start at the middle, 14. Is 14 greater or less than 7? Obviously, 14 is greater. So then it will cut it in half and go to the middle of the first half. And then it will go to 6 and say, okay, is 6 less than or greater than 7? Obviously less than. So it'll cut it in half again from here to here. And then we'll go to this middle, and it would just keep going to the middle and comparing and bouncing until it finds what it's looking for, or it doesn't. So if I bounce now back over to VS Code, okay, so here's the logarithmic one that I wrote out. As you can see, this is the exact same code I just showed. It's I took a screenshot of it. So we have an array of size 5. There are 5 elements here. And an array of size 100,000. So we are looking for 10 in this, which is right here, and 664,053 in this range. And we're going to run the code 10,000 times and time how long it will take. So if I run it, algorithmic, you'll see that we have 0.0039 seconds compared to 0.0337. As you can see, it took much longer to do, but not quite double, just one factor of 10 over. So it shows you that O of log n is pretty good. You would be very well off having an algorithm take O of log n in a coding interview. Okay, so going back over to the slides. Okay, so next is linear. So O of n means that the output is directly proportionate to the input. When making a program, you typically want to keep your time complexity at or below this level. This one's pretty self-explanatory, so I will just jump to examples. So I used a linear search as an example here. So basically, I actually cut out the if statements. I'll show you the code directly. There we go. Okay, so for linear. By the way, can everyone see the code in VS Code like pretty clear, or do I need to make it bigger?
You're good.
Looks good.
It's fine. You're good.
All right, cool. Thank you. Just wanted to make sure I wasn't. All right. Anyways, so for the linear search, it's passed a list and a number to look for, and it simply is just one for loop that goes through linearly. So 0, 1, 2, 3, 4 until it finds what it's looking for. Everyone has probably done this. I'm sure I don't need to explain it, but for the sake of understanding time complexity, I figured it might be worth it. So we have 3 lists that we'll compare of size 100, 1,000, and 10,000. And we're going to run each of them 1,000 times. And we will see the time it takes to run. So Python linear. So as you can see, to run this, each one is going to increase by a direct factor of 10. So this one is slightly slower, slightly faster than the rest, but still from 0.002 to 0.03 to 0.3 each time. And if we were to run it again, 333. Because of Python, there's always going to be some sort of balance. Like, it's going to run differently every time just because of the nature of Python. If this were to be in C, it would probably be much more consistent. But I figured the examples in Python would be very easy to follow. So yeah, so you can see that the input is directly proportionate. So if this is increased by a factor of 10 each time, and the output is increased by a factor of 10 each time. So it's directly proportionate. So then going back over, was someone going to say something?
Yeah, I was just gonna say, Connor, that pretty much goes for any kind of computer, right? Just to, I guess, differentiate theory from practicality. You know what I mean? There's always gonna be a little bit of time difference. I think
Yeah,
the
yeah.
the real idea, and for people who are, because if you're a freshman or after you've probably either taken Calc 1 or you're taking Calc 1 now, think of it almost maybe as like a limit. As you're heading towards like a certain point, you get closer and closer to that time. And on a computer,
Yes.
because it's real life, it's not theory, it's gonna differentiate a little bit, but they call it, well, I'll let you get to it. But yeah, I kind of think of it as a limit.
No,
So
I
think
think you're exactly correct. When me and James were testing out this code and just making sure everything was going good, I actually ran a benchmark. I ran Prime 95 to stress my CPU to see if it would slow it down, and it did, like, tremendously. So it definitely takes into account like what speed your computer is, what's running in the background, all that. But the point is, faster code will always run faster on anything.
exactly.
Comparatively. Thank you for that. And I'll go back to the presentation. Okay. And lastly, of the four major ones, we're going to cover quadratic time. So quadratic time is really bad. It means that for every input, there must be two operations ran. So this one is very important to memorize so that during coding interviews, you know how to avoid it and optimize your code further. So pretty much during a coding interview, there will always be some sort of easy way to get the answer correct that they're pretty much waiting for you to do as bait. So if there's an O of n squared way to do it, you can do it that way, but during a coding interview, they're going to be looking for the people who can take that O of n squared and make it much faster and try to go for O of like log n, or even just like any sort of increase. So let's look here. So the insertion sort is worst case O of n squared. So this code here is going to sort through an array that's passed. So it's going to have one for loop here. It's going to get a key, and then another a while loop inside of that. So for everything it has to go through in this for loop, it's going to have to loop again. So if I bounce over to Visual Studio again. All right, so here's the quadratic example I chose. So here's the exact code I just showed you for the function. So I chose to do 3 arrays, so one of size 5, one of this length, it's quite a lot, and one of this length, much bigger. So then we're going to run each of these 100,000 times, and I've tested this, so it should be good. It doesn't seem like there's any sort of memory issues, so I'll run it, and now we'll see the output here. So you see it's taking quite a lot of time to run. So for the first one, it was only 5 elements. So it ran at 0.07 seconds. The second one was a bit more. I don't know exactly how many. Just copy and pasted the numbers. And it's 0.28. So you can see it's already it's taking a factor of 10. Well, it's taking a lot longer to run. And for this other extremely long one, it took 2.4 seconds. So you can see this is exactly like a parabola. It is going up just quadratically. That's why it's called quadratic. So back into the slides. Okay. All right. So now we're going to talk about big O notation. Simply put, big O notation is a notation that computer scientists use in order to approximate the amount of time and or resources a program will take up. There are actually different types of notations that you will or have learned about These are big O notation, which represents the worst case, big omega notation, which represents the best case, and big theta notation, which represents the average case. So let's talk about big O first. Big O is a measure of the longest amount of time it could possibly take for the algorithm to complete. This is the most widely used one because it is very useful for actual software engineering. Not every scenario will be the best case scenario. In fact, sometimes it will actually be the worst case. Sorry for the pessimism. It is important to think about how things can go wrong so you can prevent them from going wrong. Big omega takes the least amount of time and resources. This is you banking on the program and the input to be absolutely perfect and that nothing can go wrong. Big omega is very important for trying to find which inputs an algorithm will handle better than others, as you will or have done in 403. Put simply, big theta is the average case, so it will always be between big O and big omega. I'm not going to go too deep into this, but when you take 403, you're going to see these graphs a lot. It's all about finding where these 2 points get closest. Okay, so now we've talked a lot about like the literals, the actual definitions, but how do you eyeball time complexity? You're going to want to be able to figure out what the time complexity of code is quick during coding interviews or during tests. So the easiest way to do this is to choose one statement and use it as a counter. If you are looking for worst case, then you want to walk yourself through the algorithm and follow the path that will take the longest. Inversely, if you are looking for the best case, you want to walk through the algorithm and find the fastest way to break out of it. So this is a constant algorithm, right? This is just pseudocode, means nothing. Let's just pretend that this is like a print statement or something, right? So you pass it n, a simple, like one number, and then no matter what n is here, this is just going to do one operation, right? So this would be constant O of 1. Then for linear, you're passed a number n, and you're doing a for loop from 0 to n. So this is going to be linear because for every n you put in, you're going to be doing another operation. So this operation is getting ran n times, which is directly proportionate to how big n is. Okay, and then we have quadratic here. And so if we have the constant time operation inside 2 for loops, the first for loop is going to be... Okay. The first for loop is going to be of size n. So for every number, or for every size of n, you're going to have to run through another for loop n times inside that. So it is going to be ran n squared times, which means quadratic. So we have quadratic with conditionals, right? So this is where you start to look at the difference between worst case and best case. So here, if you're past n, if something about n, doesn't matter what it is, if something is true, right, then you're going to do this O of n squared operation here that's inside this if statement. So this is a double for loop with a constant time operation. So you're going to say, okay, so worst case scenario, if this, whatever this is here, is true, we are going to be going through this n squared times. But on the other hand, if you are going for best case, right, so pretend this isn't true, and we're always going to do this else here, this is going to be O of n, because it's just a single for loop. So this one actually has 2 different ones depending on this if statement. So you would say, worst case, O of n squared, best case, O of n. So that's how you would have the difference. Now here, linear with a constant scale. So for each, if you're past n, for every n, or you're going to multiply n by 5, so you would go between 1 and 5 times n. So this is still going to be linear, but it is going to be scaled. So you definitely want to watch out for that, because it's not necessarily going to be n squared, because it's not squared by itself, but it is going to definitely be longer than your standard linear. But down here, this is true for everything that is not 0, because for each 0 times n down here, that's not going to run, or at most just 1. So that's going to be, that is just going to be constant. This entire thing here will be constant, because no matter what n you pass, it's only going to run 0 or 1 times, depending on which language you're using. Okay, so we're going to do an example together. So I'd like some people, preferably not eBoard members, preferably someone that is just watching, to come along and try to figure out what the time complexity of the bubble sort is. So if anyone wants to volunteer, now would be the time. If not, I will go through it myself.
Or you could allow eBoard members to volunteer.
I'll allow James to volunteer.
Wow, what an honor.
or any other eBoard member.
So essentially, I take one look at this and I say, look, it's a double for loop. There's a for loop inside of a for loop. Therefore, this will be O of n squared time. That's essentially my eyeball process. For loop inside of for loop means O of n squared time. Of course, not always, but most of the time, that's how you would eyeball something like this. So final answer, O of n squared time.
And what do you know it? That's correct. Okay, so we're going to do this again. This is actually the same algorithm. However, this one has a flag inside the inner loop. So this is just pseudocode. So if you can follow along here, it's past a list, and n is going to be the length of the list. So we have a Boolean flag here swapped. So it's set to false. So there's the one for loop that's going to run from 1 to n. And then inside here, it's going to do a swap. So it's going to swap index I minus 1 with I. So basically, down here, it's going to be set swapped is equal to true if it swaps. So then if, where is the flag? Okay, so it's repeating if
until not swapped down at the bottom.
Where? Okay,
it's weird.
Okay. Yeah, weird pseudocode. So basically, it's going to run until swapped is until it's false, right? No, until it's true. Until not swapped. Okay, yeah, it's going to run until it's false. So then basically you can break out of the O of n squared that the bubble sort usually is if you add this flag here, because it's going to stop, in a best case scenario, it's going to stop before having to do all of these loops every time. So basically you can bring it down from O of n squared to O of n just by having a flag. So there are always ways to improve time complexity.
I think it would be helpful if we went back to the last slide and showed off best case for the previous implementation.
Okay.
So in this case, if you want to go over what the best case is, you have to take into consideration, first of all, what we're marking as our constant time, as our time complexity marker. So we're going to mark that if statement as our statement that we're going to be tracking and counting the number of times it executes. And we see that even in the best case, we're still going through the entire array twice with the double for loops. Even if we end early, we could end up accidentally swapping it into the right position after only one pass through the array. But the chances are that that's not what's going to happen most of the time. But in the best case, it's certainly feasible. But we're still using 2 for loops to go through the entire thing, which means best case, this one is also O of n squared. But in the next case, where we have the while loop, or the what's it until loop, in this case, because we have this flag here, we only have to go through the array once, and there's a chance that now we're able to break out of this loop early. And because we're allowed to break out of this loop early, if we look at what the best case is, we're only going through that inner for loop once. And then swapped is being set to true on the first go pass through of this inner for loop. And then you're breaking. So it's this repeat until is not even doing anything. It's never repeating. And then you have best case O of n time instead, essentially. That's my view of this.
So what you're saying is, like, big O will always be the same, but adding this will allow you to like have a different big omega, right?
So yes, technically this is big omega, but you're gonna see this is a weird notational thing in computer science. You'll see people just not use big omega and use big O to reference best case time instead. You'll see people say, "Oh, the best case time is O of n," even though technically they should be using omega notation, but they don't. It's kind of an annoyance, but just know that in the literature out there, you're gonna see people refer to this in all sorts of ways.
Gotcha.
I've seen lots of stuff, and even at the end, we're gonna see that they refer to best case scenarios in terms of O of n time rather than omega of n time. So
Gotcha.
yes, sorry, Connor.
No, it's okay. So I figured it would be helpful to see the time complexities of popular array sorting algorithms. So as you can see here, the best time complexities are going to be like n log n. Typically, the best ones you can get are down here: bucket sort, radix sort, counting sort. But so you're always going to want to watch out for the worst case of these, because in like your typical bubble sort, insertion sort, and selection sorts, they're all O of n squared, so they could take quite a lot of time to run. So you're going to want to have to find a balance. So up here, like your merge sorts, you see these are they're orange to represent that they're not the best, but overall they're going to be on average better, because you'd rather have it all run at n log n than have some run it like linear and some run it like the worst case run it quadratic. It depends on what you're going for, but if you're in actually in the field and writing an algorithm for your company, you're probably going to want to go for the more balanced approach so that there's no major errors. And then also, we're going to look at the popular data structure time complexities. So I'm going to provide a link at the end that will be basically like a cheat sheet for all of these. So your time complexities of the most popular data structures are a lot of them are log n, a lot of them are O of n, but my favorite one typically hash tables. So you basically get your search, your insertion, and deletion are all O of 1. They're going to be constant time because there's a specific memory address for all entries. So basically, my favorite way to think in a coding interview is if you can implement a hash table in there somehow, you should probably do it. Most of the time, that holds true. I took one interview for Amazon before I took 403, and I 100% did an O of n squared solution, and then did research online on the problem afterwards and found that adding a hash table would bring it down to, I think, log n, and that is probably why I'm not currently employed at Amazon right now. So you're definitely going to want to study up your data structures and learn how to improve your algorithm times.
I'd like to follow up comment on that. That literally, that's what Connor just said is like actually like the number one thing that they're going to check during a coding interview. There's always going to be a trivial O of n squared solution that has O of n squared time complexity. And the solution to get it down to an O of n solution is almost always to use a hash table for something. And hash tables go by many names. In Python, they're called dictionaries. In JavaScript, you can use object accesses, which is also kind of dictionaries at the same time. They're very similar, where these are all O of n. These are all O of 1 constant time operations, basically. And that allows you to basically be super cheaty and get your algorithm down from O of n squared time to essentially normally there would be a problem where an inner loop would be required to search. But because hash tables have O of 1 search, you're able to cheese the inner for loop and get constant time in search, and then basically just have an O of 1 time or O of n time solution. So that's very important, and I think everyone would do well to remember that in your time of coding interviews, that keep the hash tables in the back of your mind. Always pull them out.
They are honestly typically always your best bet.
Hash tables in Java is hash maps, yes.
Yeah, so when you think about like hash tables, hash maps, whatever it's named in the particular language, you always think about key value pairs because that's really what underlies the hash table and
Yeah.
why it's pretty much so good at it. You have a key, you put in that key, and it gets the accompanying value in whatever you're using, dictionary, hash table, etc. Through some work on the inside. You might not know it, you might have written it, whatever, but it does that in constant time.
Yeah, entirely correct. So now, if I
I
remember
have a
correctly,
question.
yeah, sure.
So in Java, I've seen hash tables and hash maps used like interchangeably, and I'm just wondering like what's the difference between the two?
Off the top of my head from Java, I remember using. I don't
Believe one of them
think I
you can
ever.
only store a value, and one of them you can store objects, if I'm not mistaken. But maybe I'm just pulling it out of my ass.
That
You can store objects in hash maps.
yeah.
Okay.
Yeah, I'm pretty sure you can. I was talking about this a little while ago with somebody. Pretty positive you can.
Hashmap is the newer version of Hashtable. Hashtable
Okay.
is old and it doesn't have as good threading support. So always use the Hashmap when possible because it's the newer version.
Okay, because I've seen
Okay.
that and I was like, oh, like I've seen people use hash tables and I've seen people use hash maps and I was like, but they do the same thing. So I was just wondering what like the difference
Yeah, well,
was.
maybe if you were looking online for some like on Geeks for Geeks or something, maybe the code was just old and they haven't gotten to using hash maps yet at that time. I don't know. That's a possibility.
Yeah, and another thing is, I mean, you could implement your own hash table too using your own chosen hashing algorithm.
Yeah.
So you can do that. I remember I did that when I was taking the I guess 200 level class, and that's how I really learned about that data structure rather than just using hash map. So it kind of teaches you, I guess, how to understand those different kind of data structures.
Yeah, for understanding it, definitely building your own data structure is nice, but for implementation, you don't always want to reinvent the wheel. Okay, so next we are going to do a few of the examples from our coding nights together. So I would like, if possible, for more people to attempt this because I'm trying to help you all understand it. So everyone can see this, right? Okay.
I'd just like to point out that you don't actually have to understand what the algorithm does. You just have to eyeball the time complexity of the algorithm. You don't need to have any idea of what add arrays is doing. You just have to look at the control structures, the for loops, the if statements, and make an assessment from the eyeball. This is probably a bad one because this one is using
A map.
Python list comprehension down there on line 8, which
Okay.
is O of n time, but that's might not be. This is more feasible, I would say. So let's try and analyze for worst possible.
So does anybody want to volunteer? It will only help you understand it, and you will walk away smarter, more smart.
Our n in this case is going to be the length of the string, I would say.
Isn't this like O of n squared because you should be using like a string builder?
Say that again?
What was that? Yeah.
Like O of n squared, you should be using like a string builder to concatenate.
I think I know what, David, you're talking about. So in Java, I mean, with the whole thing that strings are immutable, right? Pretty much
Yeah.
when you're altering a string, you're creating essentially a new string. And that whole idea, the string builder, yeah, in Java, that's a thing that you probably should be using to, mutate strings just so, save resources. I think that might actually even might be getting into a little bit of space complexity, if I'm not mistaken, when it comes to mutating.
Yeah, that would be more. Yeah, that would definitely be
So
more
that's actually
space.
the other side of time complexity, which is space complexity, which we actually might have seen, Connor, on your the sheets that you were showing.
Mhm.
Space complexity sorting algorithm, like I think radix sort, maybe merge sort, they might use. They're pretty quick, or quicker than other algorithms, but they're not in place so-called algorithms. sorting algorithms, which means they have to use multiple, maybe whatever you use, like arrays to sort. Like they don't stay in the same. They don't use the same amount of space. They have to use more space, and that's where you get the space complexity. So it's a very good eyeball. It's not time complexity, but that's in the realm more of space complexity. So that's a pretty good comment that you made there.
I'd also like to point out that different languages have different time complexities for certain underlying things. In Python, I'm not actually sure if string concatenation is O of n time. But instead of focusing on the inner statements and whether or not string concatenation is O of n time, let's just assume that string concatenation for this example is constant time, rather than worry about whether or not it is, because what's important is if it's not, there's a way to easily get around that, which of course is just pre-allocating the amount of space that you want for your string and then returning that instead. So that would be, in that case, you're able to get it down. We could assume string concatenation for all future examples as well is constant time.
And I should also mention that for all of these examples that we're doing, this is more so eyeballing. You don't have to think about all of the very small details like that, like string concatenation. It's more important to just understand the operations, your for loops, your if statements, and all that.
There are times where it's certainly important to understand the operations. For example, if you didn't have a for loop, but you called a function called like insertion sort, which was performing insertion sort, that's going to be O of n squared then. And there are cases like that where it's depending on n. So it's, but for these examples, there's a trivial solution to string concatenation in in constant time. So it's not that big of an issue here. So for this.
Oh, would this be linear?
Yes,
like,
that was
okay,
what we were looking for.
Yeah, gotcha. I was waiting for the right time.
Okay.
They make a good point that string concatenation could be potentially non-linear.
Gotcha.
So to go over for anyone that doesn't understand, it is linear. So you're passed a string. You're going to loop through the size of the string. And regardless of whether or not you are doing this section or this section, you're always going to be doing one operation in each. So it is just the size of the string pass. So yes, it is linear. Okay. So James, do you have any other specific ones, or just click the most recent ones you think?
Yeah, just go through like the most recent ones, I would say, and we'll take a look at some of these.
Okay. So this one. Oh, yeah, no.
Ah, yes. No, wait, do that one. That's a good one.
Do this one?
This is a good example for data structures and how the set data structure. So I think Robin, me and Robin were taking a look at this during the last coding night, and this is like the most elegant solution to this.
Okay, so does anybody want to take a crack at it?
This is going to require you to at least have taken like 403, so you know the time complexities of the set data structure off the top of your head.
Isn't set similar to Hashtable? So probably like linear.
Here, well, let's see. In our popular data structures, is it on this list?
It's not going to be in there. They're not going to have it.
How unfortunate.
I think adding elements to a set is constant time.
But what about constructing a set? Constructing a set from an array. I don't expect anyone to know this off the top of their head. This is a kind of a challenging problem.
Yeah, actually, I don't think I know.
It's going to be O of n, isn't it?
Yeah, it's going to be O of n for the construction. Okay. So essentially, we're constructing the set in O of n time. That ... turns the set. It gets all of the elements in the set in constant time and puts it into the brackets represent an array. So essentially, this is turning that set into an array. And what this is doing is it's removing duplicate elements. Say that again? Your mic is kind of quiet.
Oh, is my mic on?
Someone is talking in the background and they're very quiet. I heard something about registers. Whoever said registers, you were too quiet.
No, that was my roommate. He was talking.
Oh, okay.
Turn my mic off.
Fixed.
Okay.
So constant set, creating a set from a list is constant time, and essentially that's just removing duplicate elements, and then we're basically turning the array back. We're turning the set back into an array, and then we're calling this reduce map, and this is just a reduce runs that for every single. It runs that operation for every single element. Essentially, this is just summing the array. This, you could think of this as a JavaScript equivalent of sum, and this is running in O of n time. So you're running an O of n operation followed by an O of n operation. So what's the result? Technically, it's O of 2n, but that simplifies down into O of n.
O of n.
So this is an O of n time algorithm for parity checks to figure out what the element without that doesn't match, have a matching pair in a parity array is. This was an interesting problem we solved on Monday night, actually. So
yeah, we did this at coding night. If you want to check that out, we usually do a lot of time complexity checks and efficiency checks when it comes to these little algorithms that we do on Codewars. I had done one. I think it was about O of n time, and we wanted to see if there was an easier way, and this was it. So it was a pretty good one. So if you want to check out that, those are on Mondays at 8 o'clock. Same at on Discord.
Yes, definitely attend those. All right. Okay.
this is a good one.
Yeah, we can look at this one. All right. Anybody want to take a crack at it?
Let's get best and worst case for this one.
Okay, so we can. I'll start. Anyone can jump in at any time if they have anything to say. Yep.
Can you hear me?
Yes. Hi, Carolyn.
Okay. No, I'm just making sure my headphones have a proper mic. So I just wanted to make mention, because you were talking about best case and lower bounds earlier on like the omega, and I just wanted to note that those are actually not the same thing. It's very confusing to think about sometimes, but like a lower bound is how you distinguish between those different categories of, I don't know why I'm blanking on what you call them, but going from like n to n squared. If you have a function, then that function, you define a lower and upper bound on that function, like if you can write out the function. But a best case can refer to how an algorithm can have a different time complexity based on how it runs. Like, so with binary search, if you like find the element in the very first check, then that's constant time. That's the best case. But so do you see the distinction that I'm making?
Yeah, yes.
So that's why you'll say people talk about the best case, big O, because they aren't the same thing, really. James, does that make sense to you, what I'm saying?
Yeah, that actually does make sense to me. And that's actually cleared up quite a bit, because I've wondered about that for a very long time. Why people refer to big theta and big O for best case. That's been confusing me for years. So I'm glad to hear that I just went crazy and thought that they were the same thing. And that they have very subtle differences. Yeah, they do not.
Clearly in the undergraduate classes, I don't think. So it is a very, well, actually, I mean, we did talk about it, but it is a confusing thing that I think people get mixed up a lot. So there you go.
All right, thank you, actually. Okay. Back over to this. So does anybody want to start, or should I?
I'll try. Actually, you know what? I thought I heard someone else might go for it, so I'll back off.
I'm pretty sure that's O of n, and best case is going to be basically O of 1, or normal time.
All right, let me look at it. So your best case would be, okay. So there's one if statement here. So regardless, this for loop is going to run. I want to say just O of n, because this if statement here,
it doesn't, like, you don't return any quicker.
Yeah, it's going to run regardless. This if statement here doesn't return any earlier than this return statement here. So this for loop is guaranteed to run. And the only thing I want to just check, index A and B.
Aren't you like splitting the string either way? Oh, then.
Can you say that again? I didn't really hear.
Like splitting the string, so what that be a total?
Oh, you're saying the split?
Split is O of n. It's single pass.
Perfect. Okay. So then I think it would
I
still
said
just be
O of 1 because can't index B equal index A? And then it'll only go through that for loop once.
That would
It's just
be
what
possible,
Carolyn
right?
was just talking about.
Yeah, yes. So if the index A and B were passed and it was like one off or equal, it would only run once. So I think, yes, your best case would be O of 1. You're correct. And worst case would be O of n. Does everybody see that? Or
Okay, so wait, just to clarify, that's the distinction between big O and big omega, right? So big omega would be O of 1, and big O would be O of n. Or am I confused?
big O would be O of n.
Call in Carolyn, the professional.
Yes, please.
Big O and big omega have a very specific definition that relates to a function when you're trying to set bounds on a function. So if you have a function that says like 100n squared plus 50, right? You want to prove that after with a large enough n, you choose your n. You say for all n's higher than that, that function will be less than n to the third more than n, right? A function with those things.
Yes.
So if you're trying to compare two functions, that's when you use big O and omega and theta for being the type bound, right? You can so for a type bound you would do it a little differently. But
so what you're saying is that for just algorithm analysis, like what we're doing, we're only using big O, and we're just saying best case and worst case big O.
Typically, we talk about big O. Computer science likes to talk about that because the worst case is always the thing they're most concerned with, right? But in terms of the best case, when you're having like a totally different time complexity because of the way the algorithm works, that can be a best case of how the algorithm is going to work.
Okay. All right. So when we're talking about this, just use big O, right?
I think that's fine.
Okay.
Yeah, because the other ones, would they get into like more looking at like asymptotic analysis and those kinds of things where it's like, you know, you're looking at n as it goes to maybe infinity or something like that and comparing it on that scale?
Exactly.
Okay. Yeah, that's a little more mathematical.
They will ask you to do that in algorithm classes, but I mean, it's important to understand that.
Yeah.
Okay. So I think we're good on this one. We'll go over a few more. This one. All right. Anybody want to try this one?
This is a good one.
It would be pretty cool if someone wants to take a crack at it.
I'll try.
You got to give them time to answer, yes.
If no one else does it, I'll do it.
Feel free.
All right, so the A1.copy, I think, is that O of n? I think.
Yes, that's O of n.
Seems to me like, I would assume O of n.
That really O of n doesn't matter because there are two loops. There's the for loop and the while loop. So that would make it, n squared and then maybe plus the n. But when we're looking at big O time, that really doesn't really matter. You know what I mean? So I would say that's O of n squared time with a little bit extra, but it doesn't really matter. So it kind of sums up to O of n squared, sorry. Just as like, if I had a function I had a function that prints 3 times, I wouldn't say it's O of 3. I would say it's O of 1 because that's actually a topic you might want to bring up, Connor. How they kind of, as you get larger and larger, you kind of disregard the smaller.
It's more for estimations rather than the exact, like printing out if you're printing out like 2 times n, we would just call that n because it's
like
still going to be linear.
A lot of times I'll see like, people get mixed up with n squared time when it's a nested for loop versus just 2 for loops or 2 loops in general, right?
Yeah.
Not nested, and they'll be like, oh, there's 2 loops. That's O of n squared. It's like, no, it's O of n. Technically, it's O of 2 of n because there's 2 of them, but they're not nested, so it's not going for like in every one in this. Like maybe you have like an array of 10 elements. For each one of those elements, do it like another 10 times. That would be the n squared.
Yes.
So it's always good to make that difference.
You make a great point. I hope everyone heard that.
I have a question.
Yeah.
So someone said that dot copy is O of n, right?
Yeah.
And then the nested loop that we have is O of n squared, right? So
yeah,
I was about to point out
time
that's
complexities. Oh.
Because rv.count is O of n and rv.remove is also O of n. So just analyzing control structure alone, you're going to get O of n squared if you're trying for that. But technically that rv.count is inside the loop and that rv.remove is also inside the loop. And that's based on the size of rv. But technically this is going to be O of n cubed, I'm pretty sure.
Python's weird with their hidden time complexities. I'm sorry.
Yeah,
it's if Matt, if you want to switch back to the time complexities for data structure sheet, I believe because this is just a normal array that we're looking at, and removing from a normal array is O of n time, and that count function is counting how many of the things are in that array. In RV, it's counting how many times val appears in RV, and if you think about how you do that, that's a single for loop.
Yeah,
so that's
linear.
also so technically, if we want, we can picture that O of RV or that RV.count being run inside of the while loop every time. So while that's true, so that's the condition actually. So yeah, that has to be run once every time, and then every time that gets run, the RV.remove gets run as well.
And remove is constant, right?
For a normal array.
Actually,
you said it was O of n, right?
O of n.
I'm pretty sure it's O of n time.
So would that be like n to the fourth at that point?
No, because technically the count and the remove are in the same block.
Yeah, it'd be the same thing as what you said earlier, where if there was another for loop down here, and it would be 2n. So they're in the same section, so they would be counted as like 2n rather than n squared.
Okay. All right. Yeah, I think I know what you're talking about. Yeah, I get that same kind of concept from that. Python is a little bit weird with their hidden time complexities. It's kind of hard to see sometimes.
Like the dot count is like a hidden loop.
Yes. Yeah, and also the for in or like if the in operator in Python, that kind of can have like if I say like in an if statement, if a certain element in this array or this list or something, pretty sure that is like what O of n is. That O of n, I think.
That is O of n because that's a search.
Yeah, so Python is definitely weird. Maybe not the greatest to be looking around for straightforward, but yeah, it is interesting looking at these hidden time. James, you always bring up those hidden time complexities that Python has like under the hood.
Yeah, there's a lot to analyze.
They do like to flatten loops into one line. So.
Yeah.
Yes.
As you can see with some of James's solutions, they are sometimes, quite often, one line. All right, we'll look at this one next. Oh, this is a longer one. Okay, everyone.
This is a good one.
Everyone take a look at it. I'll give you like a minute, and then if anyone wants to volunteer, I guess first come, first serve.
This is even better because we have the dictionary there for the hash table time complexities. Yes. Not even I know the answer to this one off the top of my head.
Oh, I'm reading through it. I'm trying to figure it out.
I'd say linear.
Can you repeat that?
Linear. O of n.
Linear? You're saying O of n? I believe that is correct because the lookup in the hash table is O of 1.
Nope, that's wrong. It's O of n squared. Dot keys returns the array of keys.
Oh, does it?
That's the trick here. That's
Does
not.
it?
You want to think that this is a trap solution, and I regret writing this algorithm because the char dict dot keys has to find all of the keys and return an array because it's not looking it up. It's going through every key it has stored and then returning the array of keys. And then you're doing in array. So actually, this might even be O of n squared. Actually, this not in char dict dot keys statement might be for the length of the keys. Yeah. So unfortunately, this is like it off the top of your head. You want to think, oh, okay, char dict is the dictionary. So we're gonna have any lookups for the dictionary is going to be constant time. But in this case, since we're calling the keys method and trying to get the array of keys, it
Every time,
throws you off. So let's just assume that to get the keys is constant time. Why not? But then that not in the array is going to be O of n time
loop.
in the O of n time. And then, so that's O of n squared. And then that final loop down there as well.
2 of n squared. I mean,
it's going to be n squared as well. Or just normal
n.
Yeah. So the entire algorithm is n squared.
I guess the lesson to learn here is to not just assume everything is O of 1 when you're using a hash map.
Yeah. Definitely think about your
also know your language. If I were to write this in Java, I probably wouldn't. I feel like Python has the not in, makes it much easier to look at.
In operator is the most atrocious thing for estimating time complexity in the entire world because the in operator hides linear statements in for loops and can turn a normal for loop into an O of n squared loop instead.
Could you do let me see. Could you do if char dict sub char and assuming that actually 1 second. Let me see. Nah, I think it would be the same. Never mind.
If you were using, so the way that you fix this is if you have a reversible hash map, if you have a what do they call it, a bidirectional hash table where you can get from the keys to the values and from the values to the keys, then you would be able to do char in the keys essentially, and then that would be a search on the keys in the other direction. So that would be constant time. So the solution to this is to actually use a bidirectional hash map. So then this would be O of 1 time. Or O of n time. Right? My bad. Yes, not constant.
Not constant.
Linear. Yes.
All right, well, that was a good example. All right, I think we'll do 1 or 2 more. That good?
Yeah, it's 9 o'clock, so we can start wrapping things up.
This one. This one. Oh boy. Okay.
Do not do this one. Do not do this one under any circumstances.
Okay. This one. This one's better? Yeah.
This looks much nicer.
All right. So, same thing. First come, first serve.
Again, with the in dot keys, you can consider the in dot keys statement as being O of n time.
Would this one? Let me see. Because the get is a that's a dictionary, or what is that?
Yes, the get is a dictionary get. I'm not
that
sure
would be
why I used .get.
I'm pretty sure that would be O of 1, or I'm assuming it would be constant since it's a key value kind of data structure.
Oh, I know why I used .get.
I'm not the biggest Python person, so I would assume you are correct about that.
I would say it's O of n.
That the get would be O of 1, like lookup, right? Into the dictionary.
That cheat sheet said that search for what is it called? Hash tables is
search O of 1.
Yeah.
Yeah.
So I would assume that this would follow that.
Yeah, because I'm thinking anything with a key value kind of structure would be O of 1. If it is O of 1, I think it's going to be O of n.
The d.get is O of 1.
Yeah. So
that right
I would say O of n or O of 2n if you want to be more specific. But yeah, it'd be linear time, unless I'm missing something which I didn't see.
I think it would be
And
O
you
of
said,
n
and you said the
squared.
dot keys is
Yeah,
O
that's what he's missing.
of n's. Yeah.
Yeah.
Oh,
This
that is
statement right here. So the keys method itself might be linear. I'm not or it might be constant. I'm not entirely sure, but assuming it's constant time, the issue is the fact that you have the in operator for the. Oh no, wait, hang on, that is linear. I'm mental. He's right.
Yes.
I
So
thought
you said
it was an
keys
if statement. This isn't an if statement. This is a for loop.
Yeah,
So
that's why they kind of like negate, or not negate, but it's just like, oh, it's for loop anyway.
Okay. Well,
it depends
then,
on how is keys represented. How it depends really on the internal representation of Python. Honestly, this could be solved with a Google search. Is dot keys linear time? Object dot keys time complexity. It's O of n. Wait, that's the wrong. That's in JavaScript. But what about Python? That's the real question we want to know, because everyone implements their stuff differently. Key in d dot keys is guaranteed to give you the same value for key in d. Oh, hang on. Oh, it's O of 1 time. Okay, wonderful.
Yes, I was right.
perfect.
I'll link the proof of that in the chat. And for the person who previously asked, the Hashmap question, that's also linked in there. The difference between Hashmap and Hashtable is also in the workshop text channel, which is 2 channels above the one we're in right now. Anyway.
Okay.
You want to do one more, Connor?
Yeah, we'll do one more. Why not? These are the ones I just clicked. Excellent. Why not? So does this one call the other one?
We'll just look at one on one singular function.
Okay. So you want to start with the top? Okay. So everyone, first come, first serve.
This is going to be kind of weird because, okay, so assume in this one that array appending is constant time in Python. I don't think it is, but just for the sake of brevity, there's so many array appends in this example that if we don't assume array appends is constant time, you're going to be sitting here for like an hour trying to figure out how different appends, and that includes the plus operator when you combine arrays with the plus for array concatenation. Just assume that that's also constant time. And there's a list comprehension in here, which is also extraordinarily painful. This probably isn't the best example. Maybe only analyze Pascal instead, rather than Pascal M.
So we'll do this one.
That's got to be O of n squared.
Yes, assuming that appending is constant, then yes.
When you fucking you old fucking shit.
Hoomst is playing the guitar.
We have musical accompaniment. It's nice.
Okay, so I think
in the background, but whatever.
Okay, so I think with that, we'll finish off with the examples. Yes, O of n squared.
I just want to point out here that this is actually a really interesting problem that I've seen come up a lot, and it's this idea that in your you have a double for loop, but the range of the second loop or the inner loop depends on the variable from the first loop. For a really long time, I incorrectly thought that these were n log n solutions. They are not. They are n squared solutions. I just want to put that out there because I have incorrectly, because you would think, when you think about this, this is generating a triangle essentially. And a triangle, when you think about n squared, normally you're thinking about a square. But on the whole, when you do an analysis of this, this is going to end up as an n squared solution. Still going to be within the bounds of n squared. This has been I for a long time was incorrect about
if
that.
you did something like I think I times 3, like for j in range I times 3, then you could do an n log n, because it's getting lower. Or wait, maybe that has to be on the auto.
Carolyn, you should come to a coding development night, and we can talk about this, because I would love to have a serious discussion about how the time complexity works with these niche cases where one loop depends on the range of the other loop. Because
I will get you an example of the times 3, so it's clear.
Thank you. Because I've been trying to figure out, like, in what cases can you get an n log n solution in these cases, and it's most of the time your n log n solutions are going to be recursive solutions. But I know there's a way to do it with for loops, and I've seen it before.
Oh yeah, divide and conquer is typically ends up
Yeah, so I would be excited to see some real examples of n log n and for loops.
Come, James.
Excellent.
All right. Where were we? Here. Okay. So here are my tips for the future. These are the tips for improving your algorithm programming ability. Know popular data structures and how they can be used to speed up performance. A possible follow-up workshop if I receive enough requests. Take 403. Practice by doing coding interview questions, and after each question, ask yourself, how could I improve this? Then try it again. Also, come to Monday coding nights and just watch YouTube videos and do this stuff in your free time. Just try to get good. And with that, any questions? Feel free.
So I don't know how, if you would agree with this, but I would recommend, if you're taking 403, I would take it with Pecco. I think he gives you a lot of challenges.
I took it with Pecco. I agree with it. I liked him very much.
Yeah. He explains things very well, and you learn a lot. So that's my pitch.
This isn't supposed to be a roast, but I took it with Herd, and I don't know the difference between best case O of n and omega n. So take that as you will.
You should take advantage of the good professors here that you can find, because
how do you spell his name?
Makes a big difference.
What's his name spelled like?
Petko Bogdanov.
Petko? As in the store?
Yes, it's with a K. That's how he says it on the first day of
class. I believe that's how you spell it in
okay.
workshop text. Carolyn, you might.
Gotcha.
I will spell the whole thing out there if you want.
No,
I wrote it out. I think that's correct.
I'll never forget that type of name.
Yeah, it's Bogdanov.
Yeah, we're good.
I'm in 403 with Wang. Has anybody had her?
I had her for, I think, 210. Wang, right?
I have her right now.
She's incredibly slow.
Yeah. Who are you guys talking about?
Wang.
Wang. I have her for discrete math.
Yeah, I had her for 210 as well.
Yeah, same.
I have her for data structures as well. It's quite quite the experience.
I got to take discrete with Muckle, which I'm sad that he's not teaching a course with the computer science department anymore for 333, because I think he did a good job too.
I loved 333. I was saddened to hear that they stopped teaching it.
I love the way that, well, I mean, they just teach it as a different course. They teach it about C. They don't do the assembly. And I also, I mean, I like FIPS, but I would miss doing all the tracing in the assembly stuff, because that's fascinating if you haven't done it before. I mean, if you're like James and you already built a MIPS assembler, when you go into it, maybe you don't get as much out of it. But if you're new to it, I thought it was a really good course to introduce that stuff.
I got a lot out even with the MIPS assembler beforehand. I got to learn all about the pipeline and everything. Oh man, that was by far the best class, by a lot.
They do go over some of that in the 404 computer organization.
Yeah, they go over pipelines now in 404.
I took that with FIPS, and I don't recall going over it in too much detail.
He made us implement it in our program.
I heard they moved it to 404 from 333.
Okay.
Yeah, because I just felt like we did it in more detail in the old 333 class. I really liked FIPS 404 class too. I think he does a good job. And he's a very, very nice professor in terms of
I
his
love
willingness
Phipps.
to help out.
No, yeah, he really
students.
does a good job, and like he tries. You could that matters a lot. At least in my opinion, when a teacher really puts out like extra effort to help.
Okay, so I don't think there are any more questions.
I was gonna say one more thing too
Yeah,
about
sure.
the YouTube videos that you said. I remember when I was taking data structures, and we were or data structure, the 213, yeah, or I was taking another school. Same thing though. I always loved watching like those visuals like on YouTube of maybe
sorting algorithms and stuff.
yeah, it's really like nice, and like if you're at all into any type of like mathematics, or you just have like an affinity for like seeing algorithms just like run like that, it is very cool to see. So if you really kind of want to understand on like a visual level, I'd really recommend looking at those because they're just really cool to watch, and also I feel like you get a better understanding of them.
Also, I want to plug a YouTube channel that I think I binged every video relating to that 403 when I was cramming for the final. I think it's To Back SWE for software engineer. I love them. I'll type it in. I'll send a link in chat. But they're pretty great at explaining all of this 403 level stuff.
So, Connor, I do have one more question for you.
Yes.
I was wondering, can you go back to when you're talking about constant at the very beginning?
All the way at the beginning? Sure.
Yeah.
Oh. How far? Here?
So what was the next thing you did? You were showing some print statements?
Yeah. I think for constant, let me just check VS Code. Yeah, it was just a printing from an array. Printing a value from an array.
The array index operation is the constant operation, not the print statement. The print statement can be variable.
Yes.
Depending on what's being printed out. But the main thing is the access is O of n time. Or O of 1 time. Oops.
So, okay, but you were printing out different numbers of things and different statements, right?
In the code that I showed,
he was indexing into different sized arrays.
Yeah, that's pretty much it. Was only printing
I see. Okay.
Yeah.
I was
basically our n was supposed to be the array size, and he just wanted to demonstrate that no matter how big your array is, whatever your index is constant. It's always going to be the same time to look up something in no matter how big your array is.
Yeah, I guess whether you're printing out like 1 or 10,000, that could be different. But
this is a random access array, is what you're.
Yes, random access.
Yeah.
Okay, so I understand now, because I was watching that and I was like, it seemed like you were printing out things a different number of times. And
oh well, if they were doing that,
in the code that I showed, it printed out 10,000 times, but it was always the same thing. So I would print out like the number 5 10,000 times, and the number 555 10,000 times. So that was just to get. Me and James were running into a problem where the code was running too fast that we couldn't actually time it without having to run the same algorithm 10,000 times.
Yeah, I understand that.
So, yeah.
Carolyn makes a compelling point, though, and the more that I think about it, now when we talk about print statements, the fact that we're printing out different sizes of number each time.
Yeah. So printing 55 would be longer than 5.
That's gonna introduce actually a small amount of time variation and have it be not constant. So ideally, you wouldn't print it in the thing; you'd just access it, and you wouldn't include the print in the timing. And I think we did that for the other ones, and we made sure to take out all the print statements. But the constant one, that was a slight oversight. I think.
Just pretend that the printing was constant, and the example holds.
Exactly.
Yeah, and it's probably the case that you're doing it fast enough, and you're doing small enough print statements that you're not going to see a difference when you time it. But
we would hope.
That's also another interesting thing about time complexity, where it's like, it sounds like a lot. It's like, say, assuming printing is O of 1, right? Constant time. if you print
Each
out a
time.
function, each time, if you print out 10,000 times each time you call it, even though 10,000 is a lot, it's still constant time because it's the same amount of steps. Like if you were to call a function, all right, what were we
if you're
saying?
calling it 10,000 times, then 10,000 can be your n, and then it's linear to that. So like if you have a loop and you say print this 10,000 times, then or print this 100 times or print this n times, then it's linear to the number of times you're printing it.
I was thinking 10,000 print statements and trying to say it's constant time. But
oh, so no, this is an interesting point, because if you have a program and you literally list out 10,000 print statements, okay, yeah, and then you have another program that's a loop that's like n times and you only print out one print statement. Yeah, if that n on that other program is less than 10,000, then your 10,000 print statements is going to take longer, right? Because you have a really big constant in there. But it's still constant to 10,000 because in your program there's no input that will change it and make it a million times or 100 times. And so those constants can overwhelm, but the point is that programs that have like these ends of the third can just get so huge so quickly based on input that it just overwhelms your system, or will take something that you think should take should be quick program might take years just because you wrote it so badly that you have these like exponential to the inputs.
I get it.
Does that make sense?
Yeah, so, it makes sense.
We ignore constants to simplify, but there are times when constants can be really a big factor.
Yeah.
In the real world.
I think I was just saying that, like, if you were to compare printing 10,000 times on like 10,000 lines versus like calling a function and passing in an n, and the n's just like 5 or something, like technically you'd say, oh yeah, that one's just like a for loop printing and that was O of n, while like it's constant if you do it like 10,000 lines.
Like, it's constant to the input is what it is.
Yeah.
So I thought that was just kind of weird. There's a lot of, I guess, stuff like that when it comes. I feel like time complexity is definitely an interesting topic, and it's fun to talk about that, but it definitely confuses me a bit. I still have a lot to learn about it.
I mean, I learned new stuff during this workshop, so don't think that you get to a point where you know it all very soon.
Ever. But actually, another interesting thing, if you're into like, I was watching, actually unrelated today. Today I was watching some videos on P versus NP problems, or the Millennium mathematics problems, and that involves like computational mathematics, and that kind of talks about it's kind of unrelated, but at the same time, the whole reason for some of these questions, it's like, you're dealing with sometimes like, like for example, like huge Sudoku puzzles. They always use that example. It's like, that's really easy for anybody, even like, a computer, to check if it's right or wrong, but it's incredibly hard to do as you go to like infinity, right? Like infinity rows, infinity columns. And I think it's just like an interesting problem to talk about.
It's not unrelated. It's very related. And when you do advanced stuff for research and you're trying to solve some of these hard problems, a lot of the things that people work towards are good approximation algorithms in order to get something down to polynomial time. So they say, if we can do something that's sort of right, or right or close enough in a reasonable amount of time that can actually be done, then that's how, like, there's a lot of work getting some of those sort of impossible problems and replacing them with approximate solution that can actually do it.
That's pretty cool. Yeah, that's actually really cool.
And it's very related. P versus NP quite literally just deals with classes of time complexity. And how... Yes, it's we didn't really cover anything over O of n squared, but all O of n squared problems are polynomial time problems. And then I believe NP was non-polynomial time? Is it? Or like just bigger, right?
Yeah, because
it's like exponential time stuff. Anything else?
Algorithm within like the NP set, and it's at least like the highest time complexity or less. That's how they define it, right?
Most likely.
They defined it because
it's been a long time since I've seen P versus NP.
Yeah, I know it's still kind of related to that, but like everything is inside NP, even those NP complete problems, they're all inside. They're subsets of it, right? Just of NP. So I guess it's like having like that upper bound of like, oh, it's either exponential or whatever the highest one is or whatever it is, or less. Like constant time, it's still in there, but it's less. I guess was what I was trying to say. Related, but kind of weirdly related.
Yes, non-deterministic polynomial time. Oh, pain. I thought it was non-polynomial time. It's non-deterministic polynomial time, which is, okay, so it has to relate, rather, it's basically if you can solve it in polynomial time. Or, you know what, we'll do a workshop on it. Yeah.
Yeah.
Do a P versus NP workshop.
I mean, that's more mathy, but it is like theoretical computer science, so it's still.
You win $1 million. Anyway, let's wrap up the workshop.
Okay, so no more questions. Okay, thank you for coming. Tell your friends about the IEEE, and I'm going to be leaving all of you with a parting gift. So I'll put the link in chat, but you're going to want to go to the bigocheatsheet.com. They have every bit of resource you'll ever need for algorithm analysis, and they sell a poster. This poster you can put on your wall, so you can wake up in the morning and think about algorithms.
And I'd like to advertise the fact that
you think about algorithms.
Connor also gets 10% of the proceeds.
Definitely not sponsored or anything.
Yeah, I wanted to state that we are not sponsored. We just love algorithms.
They had their IPO today.
Not insider trading or anything. All right, thank you everyone for coming. I hope you learned something.
Who doesn't love algorithms? Because if you're good at them, then you can get a job at Google.
And you make a lot of money.
Exactly.
So, before you send everyone on their way, Connor, I'll just do some announcements for what we have on the docket next week.
Perfect.
So next week we're going to be having So Monday night is going to be, well, you know what? Let's start with tomorrow night while we're at it. So tomorrow night is going to be side project development night, where we're just going to work on whatever side projects we want to and ask questions, libraries, the usual stuff. Monday night is going to be, again, interview practice night, which is, again, it's coding night, and we're going to be using our time complexity knowledge to analyze the algorithms we write. And that's really where we're going to do, coding interview practice and get the brain power that we need to solve these interview questions that we're going to be asked, right? And then I believe next Wednesday, Robin is going to be giving a workshop on the Vim editor, which is a very famous command line based editor, which I would like to start using instead of VS Code, because VS Code is bad and bloated. And then Thursday night is going to be an interview panel with industry leaders and companies, and they're going to come in and we are going to interview them. I believe Matt Keelan and Alana are going to be moderating that and asking them some questions, and we'll also open it up to audience questions. So if you have anything you want to ask people who are in the industry, feel free to show up to that next Thursday night. And then Friday night, again, is going to be side project development night. So that's our schedule for tomorrow and the rest of next week. So hope to see you at some of those events. Is there anything I want to say? Any questions?
Yeah, we'll be sending out notifications about all those things too.
Of course. All right. I'll hand it back to Connor to wrap up his workshop.
All right. Thank you, everyone, for coming. There is a poll now for a part 2, but let me know if you would like to go more into time complexity or data structures. And yeah, that's it. All right. Thank you, everyone, for coming. Have a good night.
Thank you.
Thank you, Connor. That was great.
Thank you. Good night.
Thanks, Connor.